Bismillahirrahmanirrahim. Good afternoon, everyone, and assalamu alaikum in the afternoon session. This is the session number 4, oral session 1. We have in this session oral presentations starting from O4 till O14. The first presenter is Dr. Ahmed Bayoumi. He is going to present his talk entitled Removal of Pharmaceuticals from Aquatic Environment Using Modified Biomaterials. Then, Dr. Hind Izzat is going to present her talk entitled Application of Natural Polymers Enhanced with Zinc Oxide and Copper Oxide as Humidity Sensor. Then Rania Badri is going to make a presentation entitled Optical Conductivity and Dielectric Properties of Plasticized Solid Polymer Electrolytes based on blends of carboxy, methyl, cellulose, sodium, and polyethylene oxide. Then Dr. Alauddin Abdel Gawad is going to present molecular interaction of fluorine-based derivatives and SARS-CoV-2. The next one is Hanan Al-Haiz. She's going to present study of the electronic properties of solid polymer electrolytes based on blends of CMC, PEO, and acetic acid. The next speaker is Dr. Ahmed Fahmi, physical and biophysical analysis of polyphenol alcohol, sodium alginate, zinc oxide composite. Once more, Dr. Alauddin Abdel Gawad is going to present computational notes on the chemical stability of flutamide. The next speaker is Zandina Izzat. She is going to present dielectric relaxation behavior and AC electrical conductivity of cellulose acetate, molybdenum trioxide nanoparticle blended film. And then Yasmin Osama is going to talk about the effect of substitution of the electronic properties of aspirin. Again, we have Mina Magdi going to present about the combination of analytical methods to evaluate the effect of humidity aging on the painting materials of icon models. Finally, Fatma Gamal is going to present the electronic properties of polyphenol alcohol, titanium dioxide, silicon dioxide nano-composite. After finishing this presentation, we will have free time for discussion and so on. Thank you very much. And now let's start our session.
Hey everybody, I'm Ahmed Bayoumi, Assistant Lecturer of Biophysics, Faculty of Science in Shams University. Our talk today will be about removal of pharmaceuticals from aquatic environment using modified biomaterials. Simply, our work aimed to removing ibuprofen pharmaceutical pollutant from aqueous environment using chitosan biopolymer modified with silica nanoparticles. Firstly, I would like to thank my supervisors from Shams University, Professor Said Mahmoud and Dr. Amina Omar, and of course Professor Medhat Ibrahim from National Research Center, who letting me to be here within the events of the second international conference on molecular modeling and spectroscopy. Let's go to our presentation, starting with our contents, including removal of pharmaceuticals, chitosan biosorbent material and its modification with silica, and chitosan silica ibuprofen interactions, theoretical approach and experimental approach, which including three techniques, FTIR, swelling studies, and EDIX technique. Then our conclusion. Finally, references, starting with ibuprofen. Ibuprofen is one of the most common pharmaceutical products belonging to non-steroidal anti-inflammatory drugs, which has analgesic effects for headache cases, and they have antipyretic effects. Ibuprofen chemically has amphiphilic structure due to its carboxylic group and its small hydrophobic chain. Also, it is an anionic structure. Removal of pharmaceuticals. There are various strategies for removing pharmaceuticals from aqueous environments, and adsorption is one of the most common strategies. Adsorption, usually defined as the process of accumulation of adsorbate material on the surface of adsorbent 1. Adsorption can be through chemical interaction between adsorbate and adsorbent materials and can be physical through formation of physical interaction between them. Chemical interaction is more specific than physical one, while physical adsorption is more favored when recycling is required. Recently, chitosan is extensively used as a biosorbent material for its unique chemical features, such as its high N content, unlike other biopolymers. Its many chelating sites like hydroxyl groups and amine groups, and also it is an economic polymer. However, chitosan to be used as a biosorbent material needs some modifications regarding its solubility in aquatic environment, its chelating sites, and increasing its specific surface area. And silica will chosen to be the modified nanoparticles due to its unique chemical features such as its advanced and large surface area, its high capability to be incorporated with biopolymers. It is an economic material. Then we will go to the chitosan silica ibuprofen interactions through two approaches. Theoretical approach, starting with building model molecules, we have three model molecules: chitosan molecule, which has four active sites, three hydroxyl groups, and one amine group, then silica, and finally ibuprofen molecule, which has terminal carboxylic group. So we have four active sites for chitosan and one active site for ibuprofen, resulting in five interaction possibilities between chitosan and ibuprofen, four physical interactions, and one chemical interaction between the amine group and the carboxyl group forming amide chemical bond. As following, the first interaction probability is here, formation of chemical bond between amine group and carboxyl group, and silica are added in the other active sites. The second interaction probability, including the physical interaction between chitosan first active site and ibuprofen, and also silica are added to the other active sites. Third interaction probability, fourth and fifth interaction possibilities. After building our molecules, geometry optimization processes at BM6 level were carried out. BM6 were chosen for its quick and quite accurate results. Then some physical parameters were calculated as following: total energy, which is used as a good indicator for structure's stability. We can see that interacting chitosan silica with ibuprofen results in structures with much lower energy and therefore much higher stability. Total dipole moment, which is a strong indicator for structure's reactivity, and it's obvious that interacting chitosan silica with ibuprofen resulting in highly reactive structures, especially the first and fourth probabilities, representing the interaction of chitosan with ibuprofen through its amine group, either chemical through chemical interaction or physical interaction. Then homo-LOMO band gap energy, referring to chemical structure, electrical conductivity, and interacting chitosan silica with ibuprofen increases electrical conductivity of the resulting structures. Then some QSR calculations are considered as following. Ionization potential is one of the important QSR parameters referring to structure's reactivity, and it's obvious that interacting chitosan silica with ibuprofen has no significant impact on ionization potential of resultant structures. Partition coefficient, one of the most important QSR parameters for especially biological applications. Partition coefficient usually defined as the ratio between the amount of a substance dissolved in an organic solvent to that dissolved in aqueous solution. Therefore, negative results indicate hydrophilic structure, while positive results indicate hydrophobic structure. It's obvious that interacting cytosine silica with ibuprofen result in quite hydrophilic structures, especially first, second, and fourth probabilities. Surface area and volume are usually considered as QSR parameters, and it is clear that the position of interacting cytosine with ibuprofen has no significant impact on the surface area as well as structure's volume. Finally, polarizability. It indicates the ability of structure to be polarized under external field, and it's clear that interacting cytosine silica with ibuprofen increases the polarizability of the resultant structures. Then, cytosine silica ibuprofen interactions through experimental approach, preparing cytosine silica microspheres through dropping cytosine silica solution into its crosslinker solution of sodium hydroxide, forming microspheres. And this is our video of preparation process. We can notice that drops of cytosine silica solution freely dropped into crosslinker solution. Then FTIR was utilized for characterizing the prepared microspheres. This is for cytosine and silica and cytosine silica microspheres. We can notice that most peaks of cytosine were present in the cytosine silica spectra. However, there are some modification and some changes occur in the spectra. Here, the presence of SiOC band and also the disappearance of SiOH band, indicating the presence of chemical interaction between cytosine and silica as well as physical interaction between them. Then, removal of pharmaceutical ibuprofen compound using cytosine silica microspheres occurred by adding cytosine silica microspheres to ibuprofen solution and then analyzing microspheres using FTIR, swelling study, and edX after 5, 10, 30, 60, 90, and 24 hours. First, characterizing the microspheres using FTIR, we can notice that spectra of cytosine silica before interacting with ibuprofen and that after interacting with ibuprofen, we can observe that there are general reduction in all peaks of cytosine silica after interacting with ibuprofen, and there is a specific reduction in CH stretching band and also in H bending band, and shifting as well from 1546 cm minus 1 to 1584 cm minus 1, referring to a strong interaction between cytosine silica microspheres and that of ibuprofen. Then we use such spectra for calculating the uptake percentage by comparing the intensity of the interested band in each bending band before and after interaction with ibuprofen using such this equation, and the results were cytosine silica succeeded in removing 72% of ibuprofen during the first 5 minutes, reaching to its maximum at 78% after only 60 minutes, stabilizing at 77% after 24 hours. Then swelling study were performed to investigate swelling swelling capabilities of chitosan silica microspheres using the well-known equation, and the results were that chitosan silica microspheres have a great swelling capabilities, reaching to maximum swelling after 1 hour and a half and stabilizing after 24 hours at 322%. Then edX was used for calculating the percentage of each component in the microspheres before and after interacting with microspheres. It's obvious that carbon percentage increased from 48.7 to 55.5%, indicating hydrophobic interaction between chitosan silica and ibuprofen solution, and also nitrogen, sodium, and silica percentages were lowered, indicating a hydrophilic and electrostatic interaction between chitosan silica and ibuprofen. Then, reaching to our conclusion, our work occurred on two approaches: theoretical approach carried out using BM6 method, which could present quite reasonable configuration for the chitosan silica ibuprofen interactions. Then it proposed that chitosan silica ibuprofen interactions would form highly stable and highly reactive structures. Also, QSR parameters ensure that chitosan silica ibuprofen structures have quite hydrophilic nature. Finally, the amine group is thought to be theoretically the most probable active site for interaction of chitosan with ibuprofen, either in complex or adsorbed state. Then experimental parts, if they are ensured that chitosan can be modified using silica through both chemical and physical interactions. Then, if the R spectra of chitosan silica ibuprofen suffer from general reduction in all its peaks and shifting in many ones, then significant reduction in NH2, NH bending, and CH stretching bands occur and observed, referring to that there are two main mechanisms for interacting chitosan with ibuprofen: electrostatic and hydrophobic mechanisms. Results of swelling and edX analysis confirm if they are spectra, and chitosan silica were succeeded in removing ibuprofen with uptake percentage up to 77% after 24 hours. Then this is our references, and thank you.
Assalamu alaikum. Good morning, everybody. I am Hind Izzat, Researcher Assistant in National Research Institute of Astronomy and Geophysics. Firstly, I would like to thank Professor Midhat Ibrahim for giving me the opportunity to contribute in this variable conference. Our thesis entitled Application of Natural Polymers Enhanced with Zinc Oxide and Copper Oxide as Humidity Sensor, under supervision of Professor Maruf Higazi, Head of Nanotechnology Unit in National Research Institute of Astronomy and Geophysics, and Professor Nadra Nada, Faculty of Women in Shams University. Our work is about studying the effect of enhancing natural polymers with some metal oxides to be used as humidity sensor. Overview of our presentation divided into introduction, computational details, building model molecule, quantitative structure analysis relationship calculations, thermodynamic properties, natural polymer metal oxide as humidity sensor, and finally our conclusion. Let's start our presentation with introduction. Natural polymers have very important properties that it's easy to handle, abundant, and cost effective. These properties make enhancing natural polymer give a good surface for interacting with other molecules. Metal oxides are the most important materials used for improving electronic properties of natural polymers, so polymer nanocomposites are promising materials used in various applications such as sensing, electronic devices, coating, catalysis, and optical application. To follow up the change in electronic properties of natural polymers interaction with metal oxides, semi-empirical calculations were conducted that it study the relation between chemical structure and physicochemical property and biological activity. In our work, we choose cellulose, chitosan, and sodium alginate as natural polymers to be modified with zinc oxide and copper oxide. All supposed structure conducted to calculate electronic properties, quantitative structure analysis relationship descriptors, and thermodynamic properties at PM6 using Segre's program. Group 1, as shown in figure 1, represents the interaction of two units of cellulose linked through oxygen atom with zinc oxide and copper oxide, one from metal atom and one from oxygen atom, which interacted with polymer through linked oxygen R. As well, group 2 shown in figure 2 represent chitosan interaction with metal oxide as zinc oxide copper oxide with the same mechanism of interaction. Also, figure 3 represents sodium alginate group with metal oxide interacted with the same mechanism. All models conducted two quantitative structure analysis relationship calculations as listed in table 1. That represented by some important descriptors as total energy, total dipole moment, ionization potential, log B, molar refractivity, molecular weight, surface area, and volume, which describe electronic properties and reactivity of conducted structures. From all QSR data, the most enhanced structure in cellulose group is cellulose copper oxide, that it has the highest total dipole moment value and the lowest value of band gap energy, which reflect its electronic properties enhancement, and also have a high surface area and low heat of formation, which make it the most possible and active structure in this group. Also for chitosan group, chitosan copper oxide follow the same behavior, which indicated that chitosan copper oxide is the most possible and enhanced structure for this group. Finally, for sodium alginate group, there is no significant change in the electronic properties when the sodium alginate interact with metal oxide. Also, thermodynamic properties were calculated for all structures at the same level of theory, as heat of formation, enthalpy, entropy, free energy, and heat capacity, against temperature ranged from 2000 to 5000 Kelvin, which describe the thermal stability of conducted structures. For cellulose data, the most thermally stable structures was cellulose copper oxide, that it have thermally stable behavior with temperature increasing. As well, the most thermally stable structures for chitosan group was chitosan copper oxide, that it recorded stable thermal behavior with temperature increasing. While for sodium alginate group, the interaction of sodium alginate with metal oxide recorded unstable behavior with increasing temperature. So from all thermodynamic properties of all groups, we can conclude that the most enhanced and thermally stable structure was chitosan copper oxide. So we choose chitosan copper oxide to be applied as humidity sensor. Simply, sensing idea is that when a sensor surface interact with detected material, the band gap changes and the electrical properties change as well to give alarm. This interaction simulated by weak interaction between sensor surface and detected material. So for applying chitosan copper oxide as sensor, we considered a model of 3 water molecules interacted with ketosane copper oxide surface, as shown. And then we calculated HOMO-LUMO band gap energy, total dipole moment, and molecular electrostatic potential to follow up the change in electronic properties. Total dipole moment increased with decreasing in band gap. Also, molecular electrostatic potential recorded a change in map colors, which confirmed that ketosane copper oxide could act as humidity sensor. So we can conclude our work as follows. Interaction of natural polymer with metal oxide enhance electronic properties and thermal stability. Ketosane copper oxide nanocomposite could be able used as cheap and easy handled humidity sensor. Thanks all of you for attention.
Hello everybody, my name is Rania Badri Amin Sayed, Assistant Lecturer at Physics Department, Faculty of Human Ain Shams University. This is my first contribution in the second International Conference on Molecular Modeling and Spectroscopy under title Optical Conductivity and Dielectric Properties of Plasticide Solid Polymer Electrolytes based on blends of carboxymethyl cellulose sodium and polyethylene oxide. Outlines, aim of the work, introduction, sample preparation, characterization techniques, results and discussion, and conclusion. The aim of the work is to develop a low-cost membrane material with good ionic conductivity based on blends of CMC and BOO to be used in optoelectronic devices, solar cells, and sensors, and so on. We know that in the past, the liquid electrolytes was considered the main source of electrochemical power because it has a high ionic conductivity. But this type of electrolytes has a disadvantage like leakage, interaction with electrodes, which gradually corrodes the electrode materials and hence decreases the lifetime of the device. Also, the boiling point of the solvent, which limits the temperature range of the device operation. However, with the growth of solid polymer electrolytes, all this disadvantage of liquid electrolytes was disappeared, and it became possible to obtain and create new electrochemical devices, solar cells, batteries, and sensors. Because solid polymer electrolytes has excellent mechanical and thermal stability, simple preparation in different geometrical shapes, no leakage, and safety. The first to observe solid polymer electrolyte material was based on carboxymethyl cellulose sodium, and it is a natural polysaccharide polymer, has high mechanical and thermal stability and good chemical stability, and also it is non-toxic and inexpensive. This is the chemical structure represents CMC, and it is clear that CMC consists of a large number of functional groups, which increases its applications. However, polyethylene oxide is an example of synthetic polymers, and it has high thermal and mechanical stability, inexpensive and non-toxic polymer, but BO has low ionic conductivity, but we can overcome this disadvantage by blending with other polymer, adding acid or salt, and also raising the temperature, and this is the chemical structure presented as BO. Sample preparation. Solution casting method was used to prepare our solid polymer electrolyte materials that based on CMC and BOO, where pure CMC was prepared by dissolving 1 gram of CMC in 75 milliliter distilled water, and a constant weight percentage of glycerol was added to enhance the mechanical properties of the prepared films. Also, the bulk solution of pure BOO was prepared by dissolving 1 gram of BOO in 15 milliliter distilled water, and also the same percentage of glycerol was added. and hence different concentrations of CMC and BOO was mixed with each other, and we obtained the blended CMC BOO solid polymer electrolyte materials as presented in the table. Characterization technique. Ultraviolet visible spectrophotometer was used to determine the type of transition and the optical band gap energies of the prepared solid polymer electrolyte materials, and the measurement was performed at Spectroscopy department NRC. Meanwhile, to confirm that a strong interaction has been occurred between CMC and BO, and to determine the functional groups of the individual polymers, FTIR spectrophotometer was used. Also, AC conductivity, activation energy, and some dielectric properties was determined in the range from 15 Hz to 1 MHz at different temperatures via electrical impedance spectroscopy. Results and discussion. Firstly, for the optical results, the following three figures presented the changes has been occurred in the transmittance, reflectance, and extension coefficient of pure CMC and BO as a result of a blending, where it is clear from the figures that the transmittance was increased sharply with increasing wavelengths until it reaches a saturation in the visible and near IR region for pure and blended samples. Similarly for reflectance and extension coefficient. Also, the figure indicates that a strong change was happened for transmittance, reflectance, and extension coefficient of pure CMC and pure BO as a result of blending. And also that the sample B2 has the highest transmittance and the lowest reflectance, and this sample, which consists of 80% of CMC and 20% of BO. Also, the optical band gap energy was determined using David and Mott equation for pure CMC and pure BO and the blended sample. The following figure represents the variation of alpha H nu of power half with the energy, and it is observed that CMC has 3 optical band gap energies, meanwhile BO has only 2 band gap energies. And also, as a result of blending, the blended samples has 2 optical band gap energies, and the sample B2 possesses the lowest optical band gap energy. And also, the changes in the values of the optical energy gap may be attributed to the chemical bonds formed between CMC chain and BOO chain, and this change in the optical energy gaps means that CMC and BOO solid polymer electrolytes becomes more sensitive and can be used in sensing devices as a membrane material.
Good morning, ladies and gentlemen, and dear colleagues. It is a great honor to have the opportunity to participate with this plethora of scientists to highlight the remarkable contribution which molecular modeling and spectroscopy make in so many areas of our life. My topic today belongs to the serious dilemma that we are currently facing, I mean the coronavirus. So my topic is entitled Molecular Interaction of Fluorine-Based Derivatives and SARS-CoV-2. Coronavirus is a subclass of positive stranded RNA pathogens that cause mild to moderate upper respiratory illness. There are three new coronaviruses have originated from animal reservoirs. These are severe acute respiratory syndrome SARS, Middle East respiratory syndrome MERS, and coronavirus disease COVID-19. SARS is composed of four main structure protein. It is a spherical structure. This structure is composed of spike, envelope, membrane, and spike, membrane, and nucleocapsid proteins. The viral spike protein is composed of two subunits, S1 and S2. S1 is responsible for ACE2 receptor attachment, and S2 subunit is mediating membrane fusion. These S1 protein subunit attach to the receptor binding through the receptor binding domain of the virus. Source strain is engaging in attachment to the angiotensin converting enzyme in human to facilitate viral entry to target cell. We use the fluorine nanoparticles as proposed nanoparticles um, to inhibit the interaction of SARS with the ACE2. We use fluorine nanoparticles is the carbon nanostructures. The fluorine nanoparticles have unique physical and chemical properties. Fluorine has many applications in biomedicine. However, a prominent fluorine property are properties are its reactive oxygen species scavenging, while fluorine-based derivatives depend on their chemical structure to exert this scavenging activity. So, if we use what's called computational biophysics, which is one of the molecular modeling approaches and can be used to find out effective treatment of such pandemics. So, this study has been undertaken to study the molecular interaction of fluorine-based derivatives with the receptor binding domain of SARS-CoV spike through docking experimentation. Six fluoropyridine, 1 carbon dithioic acid, 2, 3, and 4 subunits, substituted benzyl ester-based derivatives at ortho, meta, and para position were used. These molecules are built with the use of Gauss view program. These compounds have been previously reported having antiviral activity. These compounds was optimized in the vacuum by PM6 semi-empirical quantum mechanical level of theory. And we use the co-crystallized structure of SARS-CoV-2 spike receptor binding domain in complex with angiotensin converting enzyme from BDB protein data bank and downloaded the The receptor binding domain was extracted from the ACE2 and N-acetylglucosamine moieties were removed. The polar hydrogen atoms were added to the protein and the stagger charges were added to each atom, and non-polar hydrogen atoms were merged to the protein structure using autodock tools. Then two different molecular docking protocols were used for predicting the binding affinity for fluorine derivatives. Autodock Vena and Dink2 server. In both protocols, the grid box has dimension 36 angstrom multiplied by and 50 angstrom and 21 angstrom in X and Y and Z dimension with grid spacing of 0.375 angstrom. The grid center was designed at dimensions for X, Y, and Z minus 30 angstrom, 29 angstrom, and 6.75 angstrom. These are the fluoropyridine derivatives used for the experiments in neta, ortho, and para positions. It is interesting these two docking protocols reveal the possibility of fluoropyridine based molecules interact with the binding site of SARS-CoV-2 spike protein. The generated complex in both protocols are ranked on the basis of energy associated with protein-linked interaction. Top-ranked binding energies in the Link2 server were taken as a response in each run. The docking results exhibit relatively high potential for binding of fluoropyridine compounds in terms of effective molecular interaction with the SARS-CoV spike receptor binding domain. The relative binding affinity between the ligands containing CN group and NH group have exhibited better binding affinity compared to the rest of compounds. The ligand stability was then assessed by monitoring the residue contribution to proteins ligand interactions. The docked complexes are analyzed by the protein ligand interaction profile to classify the types of interaction. Fluoropyridine-based molecules were surrounded in spike receptor binding domain binding site by hydrophobic interactions, pi-cation interactions, pi-pi stacking interactions, and hydrogen bonds were also observed between NH groups and tyrosine 505 amino acid residue.
Hello everybody, my name is Rania Badri Amin Sayed, Assistant Lecturer at Physics Department, Faculty of Human Ain Shams University. My second participation in the second International Conference on Molecular Modeling and Spectroscopy under title Study of the Electronic Properties of Solid Polymer Electrolytes based on blends of CMC, BO, and acetic acid. Outlines, introduction, aim of the work, calculation details, building model molecules, results and discussion and conclusion. We know that molecular modeling helps in understanding the mechanism of interaction between different materials and also used to study biopolymers and man-made polymers because it has features like accurate, save time, easy processing method, and safety. The aim of the work is to study the electronic properties of CMC, BOO, and CMC blended with BOO theoretically, and also to confirm the experimental results presented in the first presentation. The effect of blending on the electronic properties of sodium carboxymethyl cellulose, which is abbreviated as CMC, and polyethylene oxide, abbreviated as BOO, was studied theoretically using density functional theory, as implemented in Gaussian 09 package at Spectroscopy Department, National Research Center. Model molecules representing CMC and BOO are subjected to optimization at P3 lab level of theory. Building model molecule of CMC and BOO, as shown in the figure, this is the model molecule represents CMC structure, and this is that represents BOO. As we see that in the CMC structure that it contains a large number of hydroxyl group, and this is one of the most reactive functional groups present, through which CMC can interact with the BOO and form hydrogen bonding. Building model molecules of blended CMC and BO. As the shape and size of polymers plays a very important role in its electronic properties, CMC was blended with BO in different blending ratios, as trimer CMC with monomer BO, dimer CMC with dimer BO, and monomer CMC with trimer BO. So that we suppose that we have 4 units of CMC and that 4 units of BO in order to follow the same sequence presented in the first presentation that occurred in the experimental part. Results and discussion. This figure shows the 3 mechanisms of interaction between CMC and BOO, which are trimer CMC with monomer BOO, dimer CMC with dimer BOO, and monomer CMC with trimer BOO. Where here the effect of blending was discussed in terms of total dipole moment and HOMO-LOMO band gap energy as electron volt. As we know that blending of polymeric materials provides enhancement in the electronic properties of the individual polymers that were helpful for electronic applications. As we see from the table that the total dipole moment values was changed and also that the HOMO-LOMO band gap energy was decreased as a result of blending of CMC with BOO. And we see that the model molecule representing trimer CMC with monomer BOO possesses the highest total dipole moment and the lowest HOMO-LOMO band gap energy, so that we can conclude that trimer CMC with monomer BOO blend can be used as a perfect membrane material in storage devices, as it possesses total dipole moment of 40.3 dBi and HOMO-LOMO band gap energy of 0.07 electron volt. To confirm the results of total dipole moment and HOMO-LOMO band gap energies, molecular electrostatic potential was also calculated for all the studied structures at the same level of theory. Whereas we know that the reactivity of a molecule can be determined by following in its strength a color mapping. This mapping of colors refers to the distribution of electronic charges within the molecules under study and starts from red to yellow, green, and blue, where the red color refers to high electronegative side and hence highly reactive molecules, but the yellow and blue colors refers to the neutral and electron positive charges. As we see from the figure that CMC, the red color presents only around the edge of CMC, that's through the OH group presents in the terminals of CMC. Meanwhile, as a result of blending with the BO, we see that the intensity of the red color increases and it's distributed around the whole molecule, which means that the molecule becomes more reactive as a result of blending. Molecular modeling for CMC, BO, acetic acid solid polymer electrolyte material. As we see from the previous slides that the model molecule represents trimer CMC with monomer BO, possesses the highest total dipole moment and the lowest HOMO-LOMO band gap energy, then we can increase our levels of calculations by adding acetic acid to this model molecule in order to increase the reactivity and enhance the electronic properties more. where the effect of acetic acid addition on the electronic properties of CMC and BOO was studied in terms of total dipole moment and HOMO-LUMO band gap energy. However, this interaction was done throughout the hydroxyl group present in the structure of the proposed model molecule of trimer CMC with monomer BOO. Total dipole moment, HOMO-LUMO band gap energy, and molecular electrostatic potential studies for model molecules based on CMC, BOO, and acetic acid. As we see from the table that the total dipole moment increased with increasing acetic acid content up to 3 units, but it decreased at higher contents. Meanwhile, the HOMO-LUMO band gap energy has a considerable enhancement in its values, where it decreases until reaching to 0.01 electron volt, and then it starts to increase slightly at higher concentrations of acetic acid. We see that the same behavior has been obtained in the experimental section presented in the first presentation, where the conductivity increases with increasing BOO concentration until reached to a maximum value, then it starts to decrease. The same behavior has been obtained theoretically using molecular modeling, where we see that the conductivity or the reactivity increases with increasing acetic acid content up to 3 units, then it starts to decrease at higher concentrations, which means that increasing acetic acid from 1 to 3 units increases the mobility, and hence the conductivity increases, and at higher concentrations a charge carriers agglomeration has been occurred, then the conductivity decreases. Also, molecular electrostatic potential confirms this conclusion, where only a red color has been obtained around the structure representing trimer CMC, monomer BOO, and 3 units of acetic acid, and this indicates that this model molecule becomes more reactive and it can be used in sensing devices as a membrane material. Molecular modeling results indicated that the reactivity of both CMC and BOO increased as a result of blending, and also that the addition of acetic acid on the CMC BOO model molecules increases the total dipole moment to 43.2 dBi, while the HOMO-LUMO band gap energy decreased to 0.01 electron volt. And finally, it's clear that molecular modeling as a computational tool is confirming the data obtained experimentally using ultraviolet visible spectrophotometer, FTIR, and electrical impedance spectroscopy results, which confirmed that the prepared solid polymer electrolytes and the proposed model molecules representing CMC and BOO becomes more sensitive and can be used in sensing devices as a membrane material. Thank you for your attention.
Hello everybody, I am Ahmed Fahmi Hussein, Master Student, Faculty of Women in Shams University. This is my participation in the second International Conference on Molecular Modeling and Spectroscopy entitled Physical and Biophysical Analysis of Polyvinyl Alcohol Sodium Alginate Liquid Composite. Contents: we will start by introduction, calculation details, build model molecule, total dipole moment and HOMO-LUMO band gap energy, molecular electrostatic potential, calculated thermal parameters, conclusion. Introduction. Molecular modeling presents prediction of the mechanism of interaction between different materials and also used to predict some properties of the produced polymer blend. Blending process between two polymers, sodium alginate and PVA. Sodium alginate is a natural polymer, has lots of carboxyl and hydroxyl function group. Also, PVA has hydroxyl group. Blending process between polyvinyl alcohol and sodium alginate was published in a study entitled Molecular Properties of Polyvinyl Alcohol Sodium Alginate Composite by Ahmed Fahmi, Rashid Fagi, Hanan Al-Hayes, Medhat Ibrahim. There are two probabilities for the interaction between polyvinyl alcohol and sodium alginate. From the conclusion of this paper, there are terminal 1 sodium alginate 3 PVA med 1 sodium alginate is the most probable of interaction because it has the highest total dipole moment and lowest band gap energy. In the second probability, also the most probable of interaction was 3 PVA carbon number 10 to sodium alginate because it has the highest total double moment and the lowest band gap energy in this group. Calculation details. In this work, we will study effect of addition zinc oxide to PVA sodium alginate blend, so that model molecules representing PVA sodium alginate and PVA sodium alginate zinc oxide are subjected to calculation using Gaussian 09 software at Spectroscopy Department, National Research Center, Egypt. Also, physical parameters such as total dipole moment, HOMO-LUMO band gap energy, and molecular electrostatic potential are calculated at DFT-B3 lab using the basis set 6-311J dB. Moreover, QSR descriptors and some thermal parameters are computed using Segres package at PM6 level at Spectroscopy Department, National Research Center, Egypt. Building model molecule for the first group, there are two probabilities for the interaction between zinc oxide and the PVA sodium alginate blend. So that in the first probability, the interaction will be occurred through zinc atom. We show in the figure 3 units of PVA attached to carbon number 10 with 2 sodium alginate units and 1 unit of zinc oxide. Also, we show as example 3 units of PVA attached to carbon number 10 with 2 units of sodium alginate with 5 units of zinc oxide. In the second probability, the interaction may be occurred through oxygen atom, so that the interaction may be through oxygen atom, and we add 5 units of OZN as a probability. Building model molecule for the second group, as similar to the first group, there are two probabilities for the interaction. In the first probability, the interaction may be occurred through zinc atom, but with the molecular with the structure terminal 1 sodium alginate 3 unit PVA made 1 sodium alginate with 1 unit of zinc oxide addition. In the second probability, the interaction may be occurred through oxygen atom with terminal 1 sodium alginate 3 units of PVA made 1 sodium alginate with O zinc oxide, as shown, until 2 addition of 5 unit of zinc oxide in the two probability. Total dipole moment and HOMO-LUMO band gap energy. For the first group, in the first probability, it's clear that the structure 3 units of PVA carbon number 10 to sodium alginate with addition of 2 units of zinc oxide is the most probable interaction because it has the highest total dipole moment value and the lowest band gap energy value. Also, in the second probability from interaction, it's the structure 3 PVA carbon number 8 to sodium alginate, also with 2 units of zinc oxide, but the interaction through O oxygen is the most probable interaction because total dipole moment has the highest value and the band gap energy has the lowest value. Another result is in the second group. For the best probability, also the addition of 2 units of zinc oxide through and the interaction occurred through zinc atom is the most probable interaction. But the next probability, the addition of 3 units of zinc oxide and the interaction through oxygen atom is the most probable. So that we will confirm the result by electrostatic potential. Molecular electrostatic potential is show the distribution of electronegativity of orbitals within the molecule. For the first group, in the first probability as shown in the figures, with addition 1 unit of zinc oxide, the distribution of electronegativity is more than 5 units, so that its indication to the reactivity will more with no number of zinc oxide units, and is according to the result of total dipole moment. Also, the same result with the second probability of interaction. Molecular electrostatic potential for the second group results for the first probability and the second probability show the same results of distribution of electronegativity for the structures. Meanwhile, the red lines is more reactivity or more electronegativity, and red lines is neutral areas in the molecule. Thermal parameters. We will calculate some thermal parameters like enthalpy. Enthalpy is defined as sum of system's internal energy and the product of its pressure and value, and express about released or absorbed energy. So that in the first group, for the first probability, we see that the low values of enthalpy is with addition 2 units of zinc oxide to PVA sodium alginate blend. By comparison, this result with the second probability of the first group, also with the second group with first and second probability, we find that the low value is the first probability in the first group with addition 2 units of zinc oxide, and the interaction may be occurred through zinc atom. Entropy is expressed about the disorder of the material. By studying the entropy for all probabilities in first and second group, we find that the lowest value of entropy also with the first probability from the first group with addition 2 units of zinc oxide, and interaction may be occurred through zinc atom. Heat capacity is definition as the amount of energy needed to increase temperature of 1 mole of the material to 1 degree. So that by calculating the heat capacity of two groups and at first and second probability, we find that the low values of heat capacity also was at the first probability in the first group with addition 2 units of the zinc oxide, and interaction may be occurred through zinc atom. Free energy is the energy available in the system to do useful work. So that by calculation, we need energy for the two groups in the first and second probability. We see that the free energy has large value in the first probability from the second group, but also for the first probability from the first group, it has high value. Heat of formation. Heat of formation is termed as a change in heat accompanying the formation of some structure from its component. So that by calculating heat of formation for the second and the first group for first and second probability, we show different results of heat of formation, but still the high value was for the first probability from the second group with addition 2 units of sodium alginate, and the reaction may be occurred through oxygen atom. But also in the first probability for the first group, the addition of 2 units of zinc oxide and interaction may be occurred through zinc atom have large value. Conclusion. The most probable interaction was at 3 units of PVA with carbon number 10 with 2 units of sodium alginate with addition 2 units of zinc oxide, and interaction may be through zinc atom. Because the value of total dipole moment was the highest value and band gap energy was the lowest value. Also, addition of zinc oxide to the structures led to increase the reactivity. By compare the total dipole moment of PVA sodium alginate blend, and after addition zinc oxide to the blend. Electrostatic potential shows the reactivity of models and confirms the result of total type moment homolomo and give energy. Also, the calculated thermal parameters confirm the thermal stability of the blend and confirm the results of total type moment and homolomo and give energy. Thank you very much.
Good morning, my dear colleagues. My name is Ala Eldin Abdelmenem Abdelgawad. I am a researcher in Research Institute of Ophthalmology, Biophysics, and Laser Science unit. This is my second topic, and this topic is entitled Computational Notes on the Chemical Stability of Flutamide. Molecular modeling is a class of computational work that paves the way toward understanding the fate and behavior of many systems and molecules in different fields of application, and provides important physical and chemical and biological parameters. One of these very important application is the drug design. Flutamide is non-steroidal anti-androgen drug for prostate cancer treatment. The interaction of flutamide with nanoscale materials improve its pharmacokinetics as anti-cancer drug. And this work is carried out to evaluate the effect of different solvents on flutamide using the density functional theory at level P3LYP over 6.631 G dB basis set. We used density functional theory because comparing the DFT calculations and experimental values reveal the suitability of DFT technique in drug design. Flutamide is chosen as a molecule or as a model molecule and subjected to the effect of different solvents. The studied solvents were aniline, benzene, acetone, chloroform, ethanol, methanol, heptane, dimethyl sulfoxide, diethyl ether, dichloromethane, dichloroethane, toluene, water, carbon tetrachloride, tetrahydrofuran or oxolan. The calculations were performed by placing the solute in a cavity within the solvent using the default self-consistent reaction field method. The optimized parameters of solute-solvent interactions have been calculated using the DFT P3LYP over 631 G dB basis set. As we can see, remarkable interactions have been detected. In table 1 and 2, we can see hydrogen bonding characteristic, bond length, and angle for hydrogen bonding. H H10, H12, H10, H25. These are hydrogen bonding interactions. Almost in all solvents used. Moreover, an electrostatic interaction has been also detected between fluorine and oxygen. Such interactions show how to ease flutamide can be soluble in the proposed solvents. On contrary, for methanol, neither hydrogen bonding nor electrostatic interactions. Table 4 and 5 shows the reactivity of flutamides varies up and down depending on the solvent. For example, the highest flutamide reactivity is in water, while the lowest is in heptane. In water, in heptane, total dipole moment is 9.44, while in water is 11.22. And in water 4.13, the energy gap is between HOMO and LUMO energy gap is 4.13. For heptane is 4.36. Moreover, molecular electrostatic potential have been mapped on the surface of the flutamide molecule in the different solvents. Electrostatic potential, as we can see, in different solvents, is invariant. The negative regions of the electrostatic surface potential are mainly localized in both oxygen and fluorine atoms, indicating possible sites for electrophilic attacks. Thank you.
I am Dina Izzat Mahmoud. I am PhD student in Faculty of Women in Shams University, Department of Physics. This research is by Dina Izzat Mahmoud, Professor Dr. Hanan Nahas, Professor Dr. Mahmoud Al Nahas, Professor Dr. Muqtada Yusuf. The research will be the electric relaxation behavior and the AC electrical conductivity of cellulose acetate, molybdenum trioxide nanoparticle blended blend. The contents will be introduction, aim of the work, experimental techniques, results and conclusions. Cellulose acetate is a polymer which is an ester of cellulose in which the acetyl group CH3CO replaces the hydrogen bond in one or two sites in cellulose molecule, as we see in this picture. It's interested in studying this material or this polymer due to its important characteristics such as potential compatibility, good dielectric constant, excellent optical properties, excellent mechanical properties, and low cost. Molybdenum trioxide is a transition metal oxide N-type semiconductor. It has a band gap of 3.15 electron volt. It has a wide range of applications such as smart windows, gas sensor, imaging devices, electrochromic devices, photochromism. The dielectric material, when we talk about dielectric material, we talk about electrical insulator, in which in the absence of electric field the material is unpolarized, which means that the electric dipole are oriented randomly as illustrated in this figure. Upon the application of electric field, the positive charge will displace toward the direction of electric field, and the negative charge will displace in the opposite direction to the electric field. This on contrary to the electrical conductors, in which when we apply the electric field, electric current will be free. There are many polarization types occur in the material, such as interfacial or space charge polarization, and called also Maxwell-North-Sellers. This polarization occur at low frequency. The second is orientational or dipole polarization, ionic polarization, and electronic polarization, which occur at very high frequency. The aim of our work is to study the influence of blending cellulose acetate with various concentration of molybdenum trioxide nanoparticles on AC conductivity and dielectric properties toward further application of this material. The experimental technique used to prepare samples is casting method, in which the powder is dissolved in a solution by using magnetic stirrer. The second step is to pour or cast the solution in a petri dish and then put in a dryer until it completely dried, and then we eat it. LCR bridge is a device used to get important parameters such as impedance, Z, capacitance, C, phase angle phi, in order to calculate other parameters such as total conductivity and dielectric constant by know or measure the thickness of the samples and the area of the electrode. The result: total conductivity is drawn as a function of frequency and temperature, and it was observed that at low frequency the total conductivity is nearly constant and then increase with increasing the frequency. At low frequency, this behavior is like many solids and polymer, and we observe it is occurred in all our samples. The total conductivity is observed to increase also with increasing the temperature. From the interception of the total conductivity curve with y-axis, we can calculate the DC conductivity, and then we subtract the DC conductivity from the total conductivity, we get the AC conductivity. Here the AC conductivity is drawn as a function of frequency and temperature, and it was observed it is increased with temperature and also it is increased with frequency. Also, it was observed that the AC conductivity is increased with increasing the concentration of molybdenum trioxide, as we see in this figure. And by use Jones-Carr power law, this law, we can calculate the frequency exponent S from the slope of these curves. The frequency exponent is drawn here as a function of temperature, and here we observed that the frequency exponent is decreased with increasing the temperature for all our sample. This means that the correlated barrier hopping model is the dominant mechanism for the AC conduction, and so we calculate the maximum barrier height from this equation by draw a relation of 1 minus S as a function of temperature, and from the slope we get the maximum barrier height for pure surface state, zero concentration molybdenum trioxide nanoparticle, and all concentration of molybdenum trioxide nanoparticle. We observed that the maximum barrier height is slightly decreased with increase in molybdenum trioxide nanoparticle concentration. According to Arrhenius equation, we can calculate the activation energy by draw a relation between ln sigma EC as a function of reciprocal of temperature, and from the slope we can get the activation energy for all the samples. Here the activation energy is drawn as a function of frequency, and we observe that the activation energy is decreased with increasing frequency, and this occurs in all our samples, which means that the correlated barrier hopping model is the dominant mechanism for conduction. Here we draw the dielectric constant as a function of frequency and temperature, and it was observed that the dielectric constant is increased with increased temperature, and increased also with increasing the molybdenum trioxide nanoparticle concentration. According to frequency, we observed that the dielectric constant has a high value at low frequency, and decreased with increase the frequency. This we can say this is due to the dipole has sufficient time to orient with the electric field at low frequency, but at high frequency of the electric field, the dipole can't able to follow the electric field, and then the dielectric constant decrease reached saturation. This behavior in which the dielectric constant is high at low frequency can be due to the interfacial polarization, and at larger frequency it was due to Maxwell-Wigner-Seeler's polarization. By calculating the dielectric loss from this equation, we can draw the dielectric loss as a function of temperature and frequency, and we can see that there is a relaxation peak which is shifted with temperature to higher frequency. This peak mean there is a relaxation process in the material. From the relaxation, the higher frequency of relaxation peak, we can evaluate the relaxation activation energy by using Arrhenius plot, and by plot ln omega with the reciprocal of temperature, we can get the activation energy from the slope, In the onset figure, we drew the activation energy of relaxation as a function of molybdenum trioxide nanoparticle concentration, and we observed it is decreased with increasing the concentration of nanoparticles. Conclusion: AC conductivity of cellulose acetate is increased by increasing the concentration of molybdenum trioxide nanoparticles. Correlated barrier hopping model is the dominant mechanism to study AC conductivity of films. Activation energy is decreased with increasing molybdenum trioxide nanoparticles concentration. The electric constant decreased with an increase in frequency and reached the constant value at high frequency, which explained by the Maxwell-Wigner-Sellars process. The dielectric constant was observed to be higher at low frequency for all samples due to interfacial polarization. A peak in the electric loss curve is a result of relaxation process. This enhancing in AC conductivity and dielectric properties in the blended samples make the material promising to use in various applications such as electromagnetic shielding, sensors, and other nanoelectronic devices. Thank you.
Hello, my name is Yasmin Osman. I am a pharmacist in Pathology Department, National Cancer Institute. I will talk about the effect of substitutions on the electronic properties of acetyl salicylic acid. Contents are introduction, building model molecules, calculation details, structures optimization calculations, molecular electrostatic potential MESP maps, IR and Raman spectral analysis, and finally conclusion. Molecular modeling among the most promising techniques in a so-called computer-aided drug design. Contrasting the MESP maps is one of the valuable concepts in dealing with molecular modeling calculations. MESP maps is a crucial idea for evaluating the nature of chemical addition, which is most probable to be done by a certain compound, either electrophilic or nucleophilic addition. A model based on molecular modeling is established to study substitutional impact upon electronic properties of acetyl salicylic acid, which is known as aspirin. Aspirin is composed of a benzene ring terminated with a carboxyl group and an acetic acid group. It is subjected to a substitution in three sites X1, X2, X3 in order to study the impact of these possible substitutions on the physical features of aspirin derivatives and their chemical reactivity as well. X1 position was substituted with CH3, NH2, cyanide, and chloride, while position X2 and X3 were substituted with sulfur and selenium. All the studied molecules are calculated using Gaussian O9 program. Each structure was optimized with DFT at B3 lab. Physical parameters and vibrational are calculated at the same level of theory. After that, MESP maps are constructed at the same level of theory. The physical parameters that we calculated is total energy, which reflects the stability of the structure, total dipole moment, which reflects the reactivity, HOMO and LUMO band gap energy, that the energy needed to convert the structure to be a conductor. Also, we calculated geometrical parameters, bond lengths. We calculate 4 bond lengths, L1, L2, L3, L4, and bond angles. We calculated A1, A2, A3. This table illustrates the calculated physical and electronic properties. Total energy of aspirin is minus 17.6523. From the groups that substitute with X1, chloride has the lowest total energy and the most stable one. And from other position, selenium in X2 and X3 has the much lower energy and most stable compound. Total dipole moment of aspirin is 2.6570. All the substituted groups have nearly the same reactivity except chloride and cyanide in position X1 have higher reactivity and selenium in position X2 has the lowest reactivity. Band gap energy of aspirin is 0.153, but chloride in X1 has the lower value and more conductivity. Also, selenium in X3 has the lowest value and higher conductivity. This table shows the calculated geometrical parameters involving bond lengths and bond angles. Here we can conclude that the chloride has the highest value and cyanide has the lowest value compared to the groups that substitute by X1 position. And in this column, we can conclude that the sulfur and selenium has the highest value compared to the whole column. L3 also have the sulfur and selenium in position X2 have a higher values compared to their position in X3. In contrast to the results from the lens 4, the sulfur and selenium in their position X3 has a highest value compared to their results in L1, L3, sorry. Here, and from the angle 1, the highest value is from cyanide, followed by CH3 and NH2. And here the highest value is from sulfur and selenium in their position X3, and selenium in its position X2 have the lowest value. And here angle 3 have nearly the same value in the whole column. Molecular electrostatic potential MESP maps consist of different range of color extending from the red color to the dark blue, referring the red color referring to highly negative potential region, the yellow color less negative potential region, the green color natural potential region, the light blue color less positive potential regions, and the dark blue refer to the most positive potential regions. These are results for calculated MESP maps for aspirin and its derivatives. Aspirin appears as dark red color in the 3 oxygen atoms, and the upper side of the benzene ring appears as a yellow color tend to light red. The other carbon and hydrogen atom appear as light blue, and the hydrogen of the carboxyl group appear as dark blue. In the CH3 substitution leads to increase the electronegativity of benzene ring to be appear as a pale red color. In chloride, it creates a dark red color around the oxygen atom due to increase in the potential. For the cyanide, it creates a blue region around the oxygen of carboxyl group and oxygen in position X2. Also, a dark red region appears around nitrogen atom due to highly electronegativity. In NH2, it impact of redness of benzene ring, and NH2 itself has a blue and yellow color. Sulfur in X2 position strengthens the electronegativity around the oxygen atom. Benzene ring increases the possibility of the electrophilic interaction and create a blue region. But on the other hand, of sulfur in X3 position leads to weakness of electronegativity, and a red color greatly disappears except around the oxygen atom of carboxylic group. That increases the possibility to undergo a nucleophilic interaction. Selenium in position 2 or 3 follows the same pattern of sulfur. IR and Raman spectral analysis. The analysis of the vibrational spectra of the modified aspirin is an important step in this work. And here's the results of calculated IR and Raman of aspirin and its derivatives. This is the results of IR, and this is the results of Raman. Here's aspirin and sulfur in position 2, aspirin and cyanide, aspirin NH2, aspirin NH3, aspirin chloride, aspirin and sulfur in position X3, aspirin with selenium in position X2, aspirin with selenium in position X3. Conclusion. The DFT utilizing P3 lab is performed to check the electronic properties change upon functionalization. The geometrical parameters are studied in order to force the impact of substituting reactive functional groups on the geometrical structure of the resultant derivatives. MESP maps suggest that aspirin undergo electrophilic interactions via oxygen atoms and nucleophilic reactions via other positive terminals. With the same trait, all aspirin derivatives follow the same behavior with some changes owing to additive group and its site. Results showed that more indexed peaks are recorded in both IR and Raman spectra by additive sulfur, cyanide, selenium chloride groups. Such behavior may be attributed to uprising of electron rush due to electrostatic interaction of aspirin and proposed functionalization. Thank you. Any questions?
I am pleased to participate in the second conference of molecular modeling and spectroscopy. My name is Dr. Mina Magdi at the National Museum of Egyptian Civilization, NIM. My talk today is about application of the spectroscopic and molecular modeling in the culture heritage under the title A Combination of Analytical Methods to Evaluate the Effect of Humidity Aging on the Painted Materials of Icon Models. First of all, it was my pleasure to participate in the first international conference in the National Research Center. With short introduction, it is very important for the preservation of the culture heritage, and it is one of the steering principles of the NIMC for storing and display of artifacts through collaboration of different disciplines in the archaeometric research works. Our object is about icons. Icons, for the anatomy of icons, it is composed of different layers: support, wood, canvas, ground, paint layer, pigment, and binder, and the varnish layer. Our icons, it's icon of San Theodoro Shelby. Actually, our work is a second step for the previous work that included characterization of the painting materials, and the results obtained were the pigments: green ears, Persian blue, yellow ochre, vermilion, carmine lake, carbon black, gilding, and Juniperus Phoenicia wood, hemp canvas, lead white, and gypsum as ground or preparation layers, animal glue as a binder, and pine resin as a varnish. Our work can be described in three elements: design a new models, conduct artificial aging, and analyze the painting materials. We designed the models with almost of the original materials, such as vermilion, Persian blue, green ears, yellow ochre, carbon black, carmine, pine resin, lead carbonate element, with small difference, such as we used the Pinus rigida instead of Juniperus Phoenicia. We used the lead carbonate instead of based lead carbonate, and the hemp fabric is replaced with linen flax of the same group. We studied the humidity as one of the reasons for deterioration and degradation of the paint. We carried out the experiments in the humidity chamber at 85% relative humidities at different aging times: 5, 11, 15, 20, 25 days. And it is a digital photograph to focus on the color aspects as a type of comparison issue. Control before aging, after aging: 5, 11, 15, 20, 25. Infrared analysis showed there was were conformational changes within the painting materials, with a change of the vibrational frequency. And this photo is obvious, and there was a broadening of OH group, H bonded, with short hands. There is a characteristic broadening of H band as evidence of hydrational effect. Also, for the wood, there is redshift of OH and CO, cellulose and hemicellulose, For canvas, OH stretching and bending of OH. For gypsum, increase of OH and the decrease of carbonate, of lead carbonate. Also, there was a shift upward and downward of amide group, binder animal glue, and CO band of the resin. Upon the fluctuation of the environmental conditions, the hydrogen bond can be broken to induce chemical and physical changes and the deterioration of the painting. Okay, the thermal analysis showed there was a thermal stability of the etched material with the composition at a higher temperatures. To record the first order kinetics calculations and then the thermodynamic calculations by using the Horowitz-Metziger, there was a decreasing of the reaction rate constant as there is intermolecular forces between the molecules, which slowed the collision between the molecules and decreasing the value of the frequency factors. Decreasing of entropy as the products become more ordered. Positive sign of enthalpy as the product means that it is endothermic process and the energy absorbed from the surrounding area. Positive sign of Gibbs free energy, the product means the products have more energy than the reactant for further chemical reactions upon the fluctuation of the surrounding conditions. So, the non-spontaneous reactions needs more energy for the chemical interactions, and the humid conditions can provide more water molecules in the deterioration process of the painting. Also, the colorimetric measurements showed there is a decrease in the brightness index L star with increase of the color difference delta E, with darkness of the paint film, weak photostability, the humidity drives the color change in the painting. The hydrophilicity and the phase composition of the pigments lead to insertion of attract water and insertion of more waters to induce space opening and swelling and interactions with different constituents of painting materials and deterioration of the painting. Also, to ensure that it is there a significant difference in the color difference, it's by chance or there is actual difference, we used a statistical method. It didn't assume the normal distribution curve, so it didn't meet the repeated measure ANOVA. There was another method, Friedman ANOVA. It showed the rejection of the null hypothesis. There is a significant difference. We used another step, post hoc methods, by using the Bonferroni correction to locate which pairs are different at the agent 5 and 11 days with different days. Also, we studied the outer varnish layer with the water upon the water uptake, the abatic acid as the main components of the pine resin, with 1 molecule water molecule, second 3, 4, 5, 6, 7, 8. Abatic acid was 8 water molecules. It showed that there was a lowest heat of formation due to formation of new hydrogen bond with release of energy to the system level exothermic process and the formation of the new stable compound. And the highest dipole moment means that the compound becomes more polar, more reactive, more interact with the surrounding material and the change in the cystic value of the painting. Also, upon fluctuation of the environmental conditions, these bonds break to induce physicochemical interactions and deterioration and degradation of the materials through peeling and growth of the microorganism. So it's very important optimization of the different of environmental conditions, and it is recommended to be less than 85 relative humidity to avoid the damage risk of the painting materials, and use the calibrated devices to monitor the readings of the temperature and the relative humidity. Finally, I would like to thank my friend Ahmed Rubeih for design of the icon models. Our outlook, as the NEMIC contains a lot of artifacts: pottery, metals, mummies, painting, wood, bone, so it is an opportunity for more collaborations with different organizations. It is expected in the next month to a big ceremony for the transferring of the royal mummies from the National Egyptian Museum to the NEMIC. So I wish you follow this big event. I wish you visit Egypt and visit NEMIC. Thank you so much, and I hope I meet you on the third conference of molecular modeling and spectroscopy.
Electronic properties of polyvinyl alcohol, titanium dioxide, silicon dioxide, nanocomposites. This oral is presented by Fatma Gamal Ibrahim. It was published as research by research group Prof. Dr. Medhat Ibrahim, Prof. Dr. Hanan Al-Hayes, Dr. Hind Izzat, Miss Rania Badri, Miss Asma Ibrahim, Miss Dina Shhata, Miss Fatma Gamal. Article, Volume 10, Issue 5, 2020. This sample configuration shows titles about which we will talk: abstract, materials and methods, results and discussion, and finally conclusion. Abstract: physical parameters such as HOMO-LOMO band gap energy, total dipole moment, and molecular electrostatic potential are reflecting the reactivity of the given chemical structure. So, the effect of titanium dioxide and silicon dioxide upon polyvinyl chloride is studied in terms of physical properties. Model molecules for polyvinyl alcohol, titanium dioxide, silicon dioxide, polyvinyl alcohol, titanium dioxide, polyvinyl alcohol, silicon dioxide, and polyvinyl alcohol, titanium dioxide, silicon dioxide were optimized. Then, delta E, TDM, and MESP were calculated with density functional theory P3 lab with basis set LAN L2DZ. The results indicated that the reactivity of polyvinyl alcohol is improved as a result of interaction with titanium dioxide and silicon dioxide. Materials and methods. Model molecules for materials: polyvinyl alcohol, titanium dioxide, silicon dioxide, polyvinyl alcohol, titanium dioxide, polyvinyl alcohol, silicon dioxide, and polyvinyl alcohol, titanium dioxide, silicon dioxide were optimized. All calculations were carried out with Gaussian 09 program at Spectroscopy Department, National Research Center. Each structure is optimized with DFT at P3 lab together with the basis set LAN L2DZ. HOMO-LOMO energy, total dipole moment, and molecular electrostatic potential were calculated at the same level of theory. Results and discussion. The reactivity of a given structure was reported as a function of some physical parameters such as HOMO-LOMO energy, total dipole moment, and molecular electrostatic potential, as we said before. So these parameters will be calculated at P3 lab with basis set LAN L2DZ. Figure 1 presents optimized structures of Figure A, 4 units of polyvinyl alcohol, Figure B, titanium dioxide, and Figure C, silicon dioxide. First, the interaction of 4 polyvinyl alcohol with titanium dioxide. Figure 2 presents optimized structure of 4 polyvinyl alcohol, titanium dioxide. It is supposed that interaction between 4 units of polyvinyl alcohol with titanium dioxide and silicon dioxide takes place through active sites of 4 polyvinyl alcohol with different positions. The four different positions are the 4OH group of 4 polyvinyl alcohol attached to oxygen atom number 23, 25, 27, and 29, as we referred in figure 2, B1, B2, B3, and B4. For each interaction site position, only one probability for the interaction of both titanium dioxide and silicon dioxide with 4 polyvinyl alcohol is supposed. Table 1 presents the changes occurred in HOMO-LOMO energy and total dipole moment of for polyvinyl alcohol and titanium dioxide open interaction. It is found that for polyvinyl alcohol and titanium dioxide possesses HOMO-LOMO energy of 8.1463 and 1.9432 electron volt and total dipole moment of 3.1058 and 0.000 dB respectively. The HOMO-LOMO energy decreased sharply and becomes 0.5685 electron volt for the interaction of titanium dioxide with 4 polyvinyl alcohol throughout the hydrogen atom linked to oxygen atom number 29 respectively. Such a strong decrease in HOMO-LOMO energy value refers that it becomes more reactive as a result of interaction with titanium dioxide. For the same interaction position, total dipole moment of polyvinyl alcohol increased approximately to twice its value and becomes 6.7226 dB. Also, the increase in the total dipole moment values of 4 polyvinyl alcohol open interaction is considered as a strong indicator for the enhancement of the reactivity of 4 polyvinyl alcohol. Second, the interaction of 4 polyvinyl alcohol with silicon dioxide. Figure 3 presents optimized structure of 4 polyvinyl alcohol silicon dioxide at the same 4 different positions as we said before in the case of titanium dioxide. Table 2 presents the changes occurred in the HOMO-LOMO energy and total dipole moment of 4 polyvinyl alcohol and silicon dioxide open interaction. It is found that for polyvinyl alcohol and silicon dioxide possesses HOMO-LOMO energy of 8.1463 and 5.0940 electron volt and total dipole moment of 3.1058 and 0.000 dB respectively. The HOMO-LOMO energy decreased sharply and becomes 1.0721 electron volt for the interaction of silicon dioxide with 4 polyvinyl alcohol throughout the hydrogen atom linked to oxygen atom number 29. For the same interaction position, total dipole moment of polyvinyl alcohol increased approximately to twice its value and becomes 6.34546 dB. As we studied the HOMO-LOMO band gap energy and total dipole moment, we must study molecular electrostatic potential. The importance of molecular electrostatic potential in describing the electronic behavior of polymeric materials comes from its ability to describe the distribution of electronic charges within the studied molecules. Studying the MESP helps in understanding the electronic configuration and the knowledge of active sites present within the studied structures. MESP can be described by following a color map that started from red color to blue color. The red color refers to the regions very rich with electrons, which we call the active sites, while the blue one refers to that whose absence of electrons, which we called inactive sites. MESP can be mapped as contour, surface, and as total density. Figure 4 presents MESP calculated as contour for Figure A for polyvinyl alcohol, Figure B titanium dioxide, and Figure C silicon dioxide. Figure 5 presents MESP calculated as contour for polyvinyl alcohol titanium dioxide at 4 different positions which we studied before. Figure 6 presents MESP calculated as contour for polyvinyl alcohol silicon dioxide at the same 4 different positions as in the case of titanium dioxide. Third, the interaction of 4 polyvinyl alcohol with titanium dioxide, silicon dioxide, and both together. Figure 7 presents optimized structures for Figure A for polyvinyl alcohol to titanium dioxide, Figure B for polyvinyl alcohol to silicon dioxide, figure C for polyvinyl alcohol to titanium dioxide, 1 silicon dioxide, and figure D for polyvinyl alcohol to titanium dioxide to silicon dioxide. For figure 7a and 7b, table 3 presents the calculated values of HOMO-LOMO energy and total dipole moment. HOMO-LOMO energy gap decreased to 0.535 and 0.7363 electron volt for polyvinyl alcohol to titanium dioxide and for polyvinyl alcohol to silicon dioxide respectively. Total dipole moment doesn't change significantly, where it becomes 5.2086 and 4.9149 dB for polyvinyl alcohol to titanium dioxide and for polyvinyl alcohol to silicon dioxide respectively. The decreased values of HOMO-LOMO energy gap confirmed the ability of for polyvinyl alcohol to titanium dioxide and for polyvinyl alcohol to silicon dioxide structures to interact with other nanostructures. It is noted from the results that the band gap energy for polyvinyl alcohol to titanium dioxide is lower than that of for polyvinyl alcohol to silicon dioxide, which confirms that the surface of for polyvinyl alcohol to titanium dioxide is more reactive. For figure 7c and figure 7d respectively, table 3 also presents the effect of adding 1 and 2 units of silicon dioxide on the properties of for polyvinyl alcohol to titanium dioxide, where the band gap energy and total dipole moment changes to 0.5605 and 0.6351 electron volt and to 7.3745 and 12.2711 dB for polyvinyl alcohol to titanium dioxide, 1 silicon dioxide, and for polyvinyl alcohol to titanium dioxide to silicon dioxide respectively. Figure 8 presents MESP calculated as contour for the last 4 studied structures. The behavior presents in the figure confirmed that there are fluctuations in the reactivity of studied structures, where the intensity of the red color increased for polyvinyl alcohol to titanium dioxide and for polyvinyl alcohol to silicon dioxide. Conclusion. Molecular modeling at P3 lab with basis set LAN L2DZ is performed to study the mechanism of interaction of polyvinyl alcohol with titanium dioxide and silicon dioxide. It's concluded that the for polyvinyl alcohol titanium dioxide and for polyvinyl alcohol silicon dioxide and for polyvinyl alcohol to titanium dioxide to silicon dioxide polymer nanocomposite materials can be used in developing new materials for sensing devices as the structures seem to be highly reactive. It's concluded that ab initio methods based on P3 lab with basis set LAN L2DZ could be used to follow up the changes occur in the electronic properties, the distribution of charges, and the reactivity of polymeric materials. Thank you for all.
Thank you to all the presenters, to all speakers, and I'm really enjoyed with all these interesting talks. And this is the open time for discussion. Please feel free to discuss with each professor. We are going to answer all the questions, inshallah. See you in the next section. Assalamu alaikum.